All right, this video is for differentiation in class practice for Calculus 1, and this is number 13. So we did this in class today, and I had the students graph the function f of x equals e to the x, and I said, I want you to graph the derivative and tell me what you see. So here's f of x equals e to the x, and e to the x is a continuous exponential function. And the cool thing about e to the x, it's 2.71 and it keeps going. So the graph of this is really in between the two functions, y equals 2 to the x and y equals 3 to the x. So it's an exponential function, but it's in between those two. And that's why it looks like it. So I had the students graph it. So I'm going to bring up my graphing calculator. And we graphed it. And then I said, and so you should follow through if you follow along. If you hit this, you have menu. Excuse me, I don't want to do that. You want to, first of all, I want to graph it. So I'm going to Control G. I want to graph the derivative. And then I'm going to hit menu. No, I'm not. I'm going to hit this little chart thingy next to the book, and I'm going to hit where this highlighted d over d box times box. So that's the derivative with respect to x. And I want to do it on the function that I had. So I'm going to hit variable, and I'm going to hit F1 because that's the function I had of x. And when I hit enter and I graph it, I'm like, oh, I just graphed the derivative, and look, it mapped right on top of that. So that shows, and it's quite interesting, that the derivative of e to the x is itself, which is really cool. So f prime of x is also e to the x. So that is a really neat thing to know about the continuous exponential function. All right. So they look the same because they are the same. So we did that in class. Then the next thing we did is I had students graph f of x equals 2x cubed minus 4x squared plus 3x minus 1. And then I said, let's find f prime of x, f double prime of x, f triple prime of x, and f prime of x quadruple prime of x, and what can you conclude and what do you notice? So let's kind of do this. So I'm going to do f of x equals 2x cubed minus 4x squared plus 3x minus 1. And then we're going to do the first derivative. I'll use Christmas colors here. So that's going to be 6x squared using the power rule minus 8x plus 3. Okay. And then I'm going to do f double prime of x. And that's going to be 2 times 6 is 12x minus 8. And that'll be 0 there. And then I'm going to do f triple prime of x. And that'll be 12. And then we're going to go back and do f to the fourth prime of x. And when I do the derivative of 12, I get a 0. So I did all the derivatives. And what are some of the things that you notice? Well, I do notice that the highest power drops by 1 each time. That's one of the things I noticed. And so I had a cubic and then squared. So here is a power function. And I said, well, this has 2 terms to it. And it's a polynomial. And then this one is a quadratic. So it has 1 turn to it. So it has 1 turn to it. It's going to look like that. And then this one is a straight line. So this is linear. So there's no turns to that. Then this one is going to be a straight line like this, where the slope is 0. This is a constant. And when I take the derivative of the constant, I'm going to be 0. So I notice that my turns will drop each time too. So my turns will drop by 1 each time. So then I asked, well, tell me it took how many derivatives to get to 0. So if I have a power of 3, I did the fourth derivative and I had a 0. So I asked class, what if it was 2x to the 7th? And the students go, well, then it's going to take 8 derivatives to get it to a 0. So it's always going to drop by a power, but you can keep doing the derivatives until you get a 0, and it's always going to be one more than the highest power. The other thing I did show them that is sometimes when you get too many lines, you'll see it like this to the fourth x, which is these two are the same thing, saying the fourth derivative is 0. I just wanted to show them that as well. Okay. Then to continue on with this, I had them practice 41 through 44 in our Power Rule Practice Lab to show them how a different way of looking at the derivative. And we've been using like v prime and that type of thing. Well, this notation, which is a cool notation, this actually tells you can take the derivative of v with respect to r, because you're so used to doing y prime and x is your variable. This actually tells you what the variable is going to be, and the variable is going to be r, and that's what you're going to use for the power rule. So what I told everybody to do is to rewrite this so that whatever you're taking the derivative of is going to be the last thing. So I'm just going to move it here. The other thing I wanted to tell you, a, b, and c are constants, so they're numbers, all right? So I'm going to rewrite that as v equals 4/3, because that's a constant, pi is a constant, b is a constant, and then I'm going to put the r squared at the end, because that is my variable. Now I'm going to take the derivative of v with respect to r, and by doing that, I'm going to use the power rule, so then I'm going to use this and multiply that by 2, so that's going to be 8/3. Keep my constants there, and that'll be r to the first power. So that would be the derivative of the v with respect to r. So I wanted to show them that trick. So here I want to find w prime, if you will, or dw dq. I look at dq, that is my variable. That's my last one. It's all kind of set up already. So I'm just going to take dw dq. It will work just fine to take the first derivative. So this is a constant, this is a constant. So q here is to the first power, so I'm going to actually do 1 times this. So I have 3ab squared, because they're all constants. And since that's q to the 0, it goes away. So that is my first derivative. Now dy dx. Now I want to show you too is every single time we've done these already, this is like one term. Now I have 3 terms, so you can take the derivative of each one of them. So when I asked in class, okay, is this set up? Kind of everybody was hesitant because you're used to seeing this as y prime, but because I'm doing dy dx, I'm taking the derivative of y with respect to x. X is my variable. There, x is at the end of each term, except for this one's a constant. So when I do dy dx, this is just like you're used to the normal. I'm going to bring the 2 out front, so they'd be a 2a, because a is my constant, x to the first power plus x to the first times b, and that'll go to 0, and the derivative of the constant is 0. So that is the derivative of y with respect to x. Okay, now we're going to do dp dt, and I look at it. Is this set up in a form so I can take the derivative? And I'm like, oh, it would be, because the t's at the end, but it's a radical. So I want to rewrite that as t to the half power. So let's set that up. P equals a, which is a constant, plus b times t to the 1/2. Now I can go ahead and do dp dt. So the derivative of a, our constant, is 0. Then I'm going to do the derivative here. So it's going to be a half of b, t to the negative 1/2. So remember, you're subtracting 1. Then I'm going to rewrite it, dp dt. Say that fast. If I want you to rewrite it, it'd be 1/2. The b is going to stay up here, so I don't really need the 1. And that'll be a radical t down here. So that is the derivative of p with respect to t. Then this is not on your lab. So this is an extension with some formulas that we're familiar with. And there's just one typo, so I want to do that right off the bat. And this is 4/3 pi r cubed. So put a 3 there for me first before we get started. So the first one, we have the area of a circle. And they want me to find the derivative of the area with respect to the radius. And that's what the R stands for, and it's at the end. So I said, okay, I'll do that. So I'm going to find dA, dr. So that's going to be, bring down there, that's 2 pi r to the first power. And if you look at this, this is the area of a circle. And the first derivative is actually circumference. That's really interesting. So I was showing everybody. So this is the area of a circle right here. And this is circumference of a circle. Okay. Then we did dV/dr of the volume is 4/3 pi r cubed. So this is actually the volume of a sphere. So here's a sphere, a ball, if you will. And I said, okay, what is the derivative of the volume with respect to the radius? And it's already kind of set up for me. So I'm going to do dV/dr. So the 3, I'm going to multiply that times 4/3. So that would be 12/3 or 4 pi r squared. And basically what 4 pi r squared is the surface area of that sphere. And that's interesting as well. Now these last two of this in-class practice that we did was this is the formula, the volume of a cylinder. Okay, so here's a cylinder. This one is, they're both the same. But I wanted you to notice, I want you here to find VDH, meaning I want to find the derivative of the volume with respect to the height. So the height's changing here, and then here, and we're going to assume that the radius is going to stay constant. And over here, I'm asking you to find the volume, the derivative of the volume with respect to the radius. So the radius is changing and the height is going to be constant. So if I do that, I look at it, I'm doing DH, and the H is the last thing, so I can start, this is set up good to do the derivative. So this is to the first power, so I'm going to come out and do that. That's pi r squared, and which is the area of the circle here at the base of your cylinder. And the last one here is I'm going to find the dV/dr of this same thing. Well, it's, if I'm looking for the radius, I'm going to put the radius at the end. So I'm just going to write this as pi h r squared. So we're assuming that the height is constant. So if I do dV/dr, okay, it's going to be 2 pi h r, because 2 times that, and then that drops down 1. Okay, so that is, okay, so this is the area of the circle of the base. This one is really the label of that cylinder. So think of a label on a can of soup, because 2 pi r is this, is your circumference around the top here. So here's 2 pi r, and times the height. So this basically is the area of the surface area, or the label, if you will, on that cylinder, which this is all interesting, and I just kind of wanted you to see that, what the derivative stands for. So that's the end of this video on the in-class practice 13.